Okay, next exercise 34. So a group is given G and in that an element A is given. We have to prove that the centralizers of A and A inverse are actually equal. So you follow the usual strategy. You show that each set is a subset of the other. We start by showing that CA is a subset of CA inverse. So let X be any element in the centralizer of A. Then that means X commutes with A. XA is equal to AX. This implies if we pre-multiply both sides of this equation by A inverse, on this side we will have A inverse XA, and on this side A inverse and A will cancel out, we will be left with only X. So we have this A inverse XA is equal to X. Which in turn implies now we post multiply both sides by A. Doing that we get A inverse X equal to XA inverse. So we now see that X, just like it commutes with A, it also commutes with A inverse. So X belongs to the centralizer of A inverse, and hence this is a subset of this. Now note that all these things, these arguments are true for A, but A is actually any element in G. So this statement is true for every element A of G. In particular, it is also true for A inverse. In place of A, we can write A inverse. Since A belonging to G is arbitrary, we also have CA inverse, a subset of this. Which is equal to CA, because inverse of an element is the element itself in any group. Hence CA is equal to CA inverse. So the elements that commute with A are precisely also the elements that commute with A inverse. Then 35. For any group element A, and any integer k, show that the centralizer of A is a subset of the centralizer of a to the power k. Use this fact to complete the following statement. And the statement is this: in a group if X commutes with A, X is some element, A is also some element, X commutes with A, then we have to write the appropriate thing here. Is the converse true? Okay. So here we have to, unlike the previous one, here we just have to show that this is a subset of this. However, k is any integer, so keep in mind that k can be negative also. We first show this for all non-negative integers k. And for this we apply induction on k. Okay. Note that what happens when k is 0? By the definition of integral powers of group elements, this is equal to the identity of the group. Now the centralizer of the identity is actually the entire group, because every group element commutes with the identity. So we have this CA, because it's a subgroup of G, so the inclusion means the inclusion that we want to show. In fact, let's just write the actual relation is true when k is equal to 0. Assume that it is true for some non-negative integer k. Now we want to show that CA is also contained in CA to the power k plus 1. Now let G belong to CA, then G belongs to CA to the power k, that is by the induction hypothesis. Being in CA also means that the element is here. And so we have these things. So that means G commutes with both A and A to the power k. Hence G A to the power k plus 1. Using the rules of exponent, you can write A to the power k plus 1 like this. Now use the second relation to write the first two terms like this, and then here you use the first relation, and this becomes equal to this implies so CA is contained in CA to the power k plus 1. This completes the induction. Okay. This completes the induction means now our inclusion has been proved to be true for all non-negative integers k. We will now look at the case where k is negative. Next, let k be a negative integer. Then minus k is a positive integer, and we have, by what we have already proved above, this is contained in A to the power minus k. But by the previous exercise, this is the same as the centralizer of the inverse of A to the power minus k, that is this. Which is nothing but C of A to the power k. Hence, CA is contained in C of A to the power k. So that just covers all the cases. We can just write the final conclusion here. Thus CA is contained in CA to the power k for all integers k. So we can complete the statement like this. In a group, if X commutes with A, then X commutes with any integral power of A. And now finally we have also been asked whether the converse is true or not, and it turns out that the converse is not true. Let G be the group of all 2 by 2 real matrices A, B, C, D, where AD minus BC is not equal to 0, under matrix multiplication. And now in this group, we are going to look at this matrix. Note that this matrix belongs to G such that the centralizer of its second power this square turns out to be equal to the 2 by 2 identity matrix. You can calculate and see that this is the case. And so, because this is the identity matrix, every matrix commutes with the identity matrix, so this is equal to G. But the centralizer of the element itself, the matrix itself, is not equal to G, because there are matrices that don't commute with this matrix, so it cannot be entirely G, and one such matrix is this 1 0 minus 1 0. Let's just actually calculate the product, this one and the other one also, to see that they are different. 0 plus 0 0, minus 1 plus 0 minus 1, 0 plus 0, 0, 1 plus 0, 1. But if we calculate, if we change the order, zero plus 1, 1. See, in the very first element, in the first row, first column elements, the matrices are different. So they are different. 0 plus 0, 0. Minus 1 plus 0, minus 1. And 0 plus 0, 0. Oh, I think, wait, hold on. This will not work because here, okay. I cannot choose this matrix. The reason is that this matrix does not belong to G. Here AD minus BC is equal to 0. So let me just put 1 here and let's see what happens. Because I want an element in G that does not commute with this matrix. 0 minus 1 minus 1. I think it will work. 1 plus 0. Am I doing it correctly? 0 minus 1 minus 1. Oh, minus 1 plus 0 minus 1. Okay. 0 plus 0, 0, 1 plus 0, 1. So here also I have to make that change. 0 plus 1, 1. 0 plus 0, 0. Minus 1 plus 0, minus 1. Minus 1 plus 0, minus 1. Yes, they are different because again in the first row, first column elements, they are different. So the matrices are different. And in fact, let's just write this also. And hence 1, 1, minus 1, 0, it belongs to G, but it does not belong to this. So this completes the solution. The converse is not true. This contains this, but this does not contain this. Then exercise 36. Complete the partial Cayley table given below. Okay, so we have to write this table down. How many? 9. 7, 8, 9. 1 2 3 4 5 6. Oh, I need one more. 7 8. One, two, three, 4 5 6 7 8. 2 3 4 5 6 7 8. 1 4 3 6 5 8 7. 5 8 7. Okay, 4 3 6 5 8 7. Then 2. 1 7 8 6 5. 2 7 8 6 5. Okay, so here it differs. 1 8 7 5 6. 1 8 7 5 6. Then after this, here also we have 2 8 7 5 6. Okay, 7 8 6 5. Then these diagonal entries are all 1. And that's it. We have to figure out what these missing elements are, using the fact that this is going to be the Cayley table of some group. We are not going to draw the table once more. Here itself we will fill in the blank spaces. But the question is, how shall we do that? For that, there are some small calculations that need to be done. So you know that property of a Cayley table of some group, that every row and every column contains each group element exactly once. So using that and using the fact that this is going to be a group, using all the cancellation laws, we are going to figure out what these missing elements are. So now, say we don't know what 5 6 is. Okay, so suppose x is equal to 5. To avoid confusion, let's just use one symbol for the binary operation. If we don't write anything, it looks like 56. So 5 operation 6 is, say, x. Okay, then 5 is equal to now see one thing. 5 star 5 is 1. 5 star 5 is 1. And from the first row and first column, it is clear that 1 acts as the identity element. That we can clearly see, because anything you take product with 1, you get that thing back in any order. 1 star 2 is 2, 1 star 3 is 3, and so on. Like that, 2 star 1 is 2, 3 star 1 is 3, and so on. Okay, so from here, assuming that this is a group, we get this 5 equal to 5 inverse. Similarly, 6 star 6 is also equal to 1. So that also gives us 6 is equal to 6 inverse. So that means if we post multiply both sides by 6, then we should get this x star 6 is equal to 5. Now x star 6 is equal to 5. So we don't know, we want to know what x is, but x star 6 is equal to 5. So you look in the column of 6 where you are getting 5. So you see that 2 star 6 is equal to 5. So that means this is something we have seen from the table itself. 2 star 6 is equal to 5. Now, according to our assumption and according to the calculations we carried out above, we should have this. Now you use the right cancellation law to conclude that 2 is equal to x. So that means 5 star 6 will be equal to 2. To distinguish these elements, let's just write like this within a diamond. Similarly, if you calculate the other elements with a similar type of calculations, you will get these missing elements. You can verify 4, 3, then here you will have 2, 3, 4, and then 3, 4, four, 3, and finally 2. For example, let's just see one more. 7 star 6, suppose we want to find 7 star 6. So from the above calculation we see that y star 6 should be equal to 7. So in the column of 6 we see that 4 star 6 is equal to 7. So that's why 7 star 6 is 4. Okay, so that's how you get the missing elements in this table. And then the next one also has table, but there the complete table is given. We have to say some things about the group itself. I can wrap this up. Suppose G is the group defined by the following Cayley table. Again another such table. Four, 5, 6, 7, 8. One, 8, 7, 6, 5, 4, 3. 4, 3, 6, 5, 8, 7. 5, 6, 7, 8, 1, 2. 2, 7, 4, 1, 6. 1, 8, 7, 6, 5. Okay. Then 8, 3, 2, 5. 1, 2, 3, 4. Two, 3, 4. 1, 8, 7. 4, 3, 5, 6, 2, 1. So this is a Cayley table of some group. Now there are parts. A. Find the centralizer of each member of G. Part B. Find set of G, the center of G. Part C. Find the order of each element of G. Each element of G how are these orders arithmetically related to the order of the group? Okay. Now these are some things that you just have to calculate. So I straight away write the answers. It's left to you to verify that these are the things that we will get. Some of them are of course very easy. For example, since 1 acts as the identity element, so its centralizer will be the whole group, because every element of a group commutes with the identity of the group. So C of 1 is G. C of 2 is this set 1, 2, 5, 6. C of 3 is 1, 3, 5, 7. C of 4 is 1, 4, 5, 8. C of 5 turns out to be again G, just like 1. C of 6 1, 2, 5, 6. So it's just the same as 2. Then C of 7 is 1, 3, 5, 7, same as C of 3. And finally, C of 8 is 1, 4, 5, 8, the same as this one, C of 4. B. Center of G, according to the last exercise in the previous video, that is exercise 33, this is obtained by taking the intersection of all the centralizers. So you look at all the centralizers here we have calculated and see which elements are common to all of them. One of course will be there because each centralizer is a subgroup, so it must have the identity element. But besides that, you can see that here you have 5, here also you have 5, 5, 5, this is G, 5, 5, 5. So in all of them you have 5. And if you look carefully, there is no other such element that belongs to all of them. So the center is this subgroup consisting of the two elements. To verify that this is actually a subgroup, you just have to see that 5 square is 1. Yes, indeed it is 1. 5 square is equal to 1. And then in C you have to find the orders of these elements. So order of the identity is always 1. Then order of 2 is equal to 2 because 2 square is identity and 2 itself is not equal to the identity. Like that, if you keep on calculating, you will get order of 3 equal to 4, order of 4 is 2, order of 5 is 2, order of 6 is 2, order of 7 is 4, and order of 8 is 2. Why the orders of sum of the elements are 2, that we have seen. 2 to 1, the elements whose orders are equal to 2 are those for which the diagonal entries are 1. 2 square is 1 square is equal to 1. Well, except the identity, of course. For all non-identity elements, if the diagonal entry in this table is equal to 1, then that element has order 2. 2 has order 2, then 4 has order 2, 5, 6, 8. See? 2, 4, 5, 6, 8. And this is the special case of the identity element. Let's also see why order of 3 is 4. What is 3 square? 3 square gives us 5. Okay. And 3 cube is 5, 3, 5 operation 3. 5 operation 3 is 7. 3 to the power 4 is 3 cube 3. 7 operation 3, see, here we are getting 1. So until this 4th power of 3, we haven't got the identity element. Only the 4th power becomes equal to the identity element. So the order is 4. Just like that, order of 7 is also equal to 4. And finally, the relationship between these orders and the order of the group is, of course, that they all divide the order of the group. So let's just mention that and complete the solution. We observe that the order of each element divides the order of the group. Obviously, it's only an observation. We have not yet proved it generally. It generally is also true. In a finite group, if you calculate the order of any element, it must be a divisor of the order of the group. Then 38. If A and B are distinct group elements, prove that either a square is different from b square or a cube is different from b cube. Suppose none of this is true. Suppose a square is equal to b square and a cube is equal to b cube. Then a can be written as a to the power 1 by the definition of this integral power, a to the power 3 minus 2. So this is a cube, a square inverse using the rules of exponent. Now this becomes equal to, because a cube is equal to b cube, so we have b cube here. A square is equal to b square, so we have that also. A contradiction to the distinctness of A and B. So our supposition is wrong. That is, either a square is different from b square or a cube is different from b cube or both. So this completes the solution. Next, 39. Let S be a subset of a group. And let H be the intersection of all subgroups or subset of a group G, and let H be the intersection of all subgroups of G containing S, that is, that contain S. part A, prove that the subgroup generated by S is equal to H. This is one thing. And B, if S is non-empty, prove that the let me write it here, subgroup generated by S equals the set of all elements of this form S1 to the power n1, S2 to the power n2 up to Sm to the power nm, such that m is a positive integer and Si, all such Si's are coming from the set S, and the ni's, the exponents, are all integers. Okay. Now if a subset S of a group G is given, then according to this, the definition of this group, subgroup generated by S, it is the smallest subgroup that contains S, smallest subgroup of G that contains S. We have to prove that it equals the intersection of all subgroups of G containing S. So for part A, since we know that the intersection of any number of subgroups of G is again a subgroup of G so H is a subgroup of G, because H is the intersection of some subgroups of G, some special types of subgroups of G, but nevertheless subgroups of G. And the number of subgroups we are considering in this intersection, that does not matter. The intersection is always going to be a subgroup of G. In fact, we have proved this in one exercise previously. So H is a subgroup of G. Moreover, note that H is the intersection of those subgroups of G, all of which contain S as a subset in them. So that means H also contains S in it. Moreover, since H is the intersection of all subgroups sub G that contain S, we have this. Okay, so that means we have now established that H itself is a subgroup of G that contains S. Now let K be any subgroup of G that contain S. If we can show that H is contained in K, then that would just show that H is the smallest subgroup of G containing S. But that is true because in forming the intersection, that is H, K also has been considered, because we have taken all the subgroups of G containing the subset S, and their intersection we have taken, that intersection is H, and K is one such subgroup that contains S. Then by the definition of H, we have this. Hence, H is the smallest subgroup of G containing S, and so by definition H is the subgroup generated by S. Then in part B, we have to prove that if the set S is in particular non-empty, then this is true. Okay, that is, the subgroup H, its general element will look like this, which is a product of some integral powers of elements of S, where the number of factors in the product is any positive integer, and the exponents of course are any integers. So let S be non-empty. It's clear that this set is a subset of S. Why? Because you see, the elements, should I directly write like this or should I say some things to justify it? Let me write in brackets, since Si belonging to S implies Si belongs to the subgroup generated by S. Do you see what we have, why we have this thing? If you want to prove that this is a subset of this subgroup generated by S, obviously you have to show that all such products, all such elements in this set also belong to this subgroup. Now in showing that, for example, this particular element belongs to this subgroup, you just note that every Si belongs to S, and since the subgroup generated by S itself contains S, so every small Si will belong to the subgroup also. That is because we have this. So each Si belongs to this. So their integral powers will also belong to this, because this is a subgroup and it is closed under the formation of products, formation of integral powers, and products of those integral powers will also belong to this, and hence this is a subset of this. Now conversely, let G belong to S. Okay, we have to now show that G is actually equal to something like this. Then G belongs to, okay, so G belonging to S means what? G belongs to, according to part A, G belongs to all subgroups of capital G containing the subset S. Okay, instead of taking an element and proceeding like this, why don't we show that this set itself is a group, a subgroup of G containing S? Yeah, that's what we have to show. This is fine, this one contains this, that is fine, but now let us try to show that this set itself is a subgroup of G containing S. Note that S is contained in this set. Why? Because if you take any element of S, say you take S belonging to S, then S itself is a product of this form, where for M you will take M equal to 1. There is only one factor, and that factor is an integral power of S, because that is S to the power 1. So that's why every element in S is contained in this. For S1, S2, etc., Sn, T1, T2, etc., T, suppose K belonging to S and integers N, M, say P1, P2 up to Pk, we have tk pk inverse. Okay, if we can show that because these are two elements in this set, if we can show that this again belongs to the set, then by one of the results to prove that a given non-empty set is a subgroup, this will become a subgroup. Note one thing, that the non-emptiness of S is playing a role here, namely in ascertaining that this set is actually non-empty, because to prove that a subset of a group is a subgroup, you need that subset to be non-empty first of all. So that is guaranteed by this condition. So this becomes equal to SMNM. Now since we are taking inverse, so the entire order will be reversed. Also, using the laws of exponent, this will be equal to minus pk. Let me write the previous term also, tk minus 1 minus pk minus 1, like this, t1 minus p1. Now looking at this product, you see that S1, S2, etc., Sm, all the Ti's, these are after all elements of S, and N1, N2, Nm minus, although we have minus here now, but still they are integers. So this is again an expression of this form. So this belongs to the set. Okay, we are having to write the set again and again. It would have been better if we named it. Thus, Si belonging to S, this is a subgroup of G that contains S. In bracket we write, note that this subset means the set we are considering is non-empty because S is given to be non-empty. Okay, so this is a subgroup containing S. So that means the subgroup generated by S by definition will be contained in this. And yet at the same time we have also seen that this is contained in the subgroup generated by S. So the subgroup generated by S is Nm. M is positive, Si belongs to S, and Ni is an integer. So using this inclusion and the inclusion that I just wrapped up, that was here, we conclude equality. Hence, now in exercise 40, we are going to see some examples of this. In the group, of integers, of course under addition, because under multiplication the integers don't form a group. Find these things. The subgroup generated by 8 and 40. Ideally we should write like this, because the thing inside within these angular brackets should be a set. But by abuse of notation, we can also write like this, because after all the elements are going to matter. They mean the same thing. So what will this be? Then B, the subgroup generated by 8 and 13. C, the subgroup generated by 6 and 15. D. If you look carefully, this concept of subgroup generated by a subset is a generalization of the cyclic subgroup generated by a single element, because if S becomes the singleton set consisting of only one element, then you would be considering what here? Integral powers of only that element, because that is the only element available in S, and that is just by definition the cyclic subgroup generated by that single element. So this is a generalization of the cyclic subgroup concept. Instead of generating a subgroup by a single element, here we are generating a subgroup by a set of elements. M and N. E. Okay, here we have 3 elements, 12, 18 and 45, and also there is something else. In each case, in each part, find an integer k. Find an integer k such that the subgroup is actually the cyclic subgroup generated by K. We have already seen this before. In the additive group of integers, every subgroup is in fact a cyclic subgroup generated by some element, and we also know what that element is. That is the smallest positive integer contained in the subgroup, except of course the trivial group where there is only 1 0 which has no positive integer. Any other subgroup of Z must contain at least one non-zero integer, and hence it must contain a positive integer. If you find the smallest positive integer in that subgroup, that one will generate the subgroup. Every subgroup of this group is cyclic. There is no non-cyclic subgroup, because the group itself is cyclic. No, every subgroup of a cyclic group is cyclic, so from there this result is coming. So without writing too much, we will just simply mention the things. The subgroup generated by 8 and 14 will contain 2 times 8 minus 14, that is equal to 2. Or in fact, I think I should write some things. Let's not just leave things like this all the time. Note that (8) and 14, both of them of course belong to this, because by definition it's the subgroup generated by the set 8, 14. So it will contain the set in it as a subset. So 8 and 14 both will be elements in this subgroup. And belongs to this. Okay. Suppose 1 belongs to this. Now a general element in this will look like what? From this exercise we see that a general element looks like this. But since we are in an additive group, this actually is equal to 8n1 plus 14n2. Okay. So that means 1 will also be an element of that form. 8n plus 14n for some integers n and m. But then, since the right hand side is an even integer, the left hand side should also be divisible by 2, which is a contradiction. 2 divides 1. A contradiction. Thus 1 does not belong to 8 and 14. That is, 2 is the smallest positive integer in this. Hence, this is actually equal to the cyclic subgroup generated by 2. So there were many things to write, so I was just simply leaving it like that. B. In B we have 8 and 13. Note that (8) and 13 both of course belong to the subgroup generated by them, and one is equal to 3 times 13 minus 6 times 8. No, I think what? 39. No, this is not correct. Okay, let me just, I can't seem to be able to do these calculations very quickly. It's always a problem with me. So 1 is 3 minus 2, 3 minus 5 minus 3, so 2 into 3 minus 5, then 2 times 3 minus 8 minus 3, 3 times 3 minus 8, minus 13 minus 5. 3 times 3 minus 8. Okay. Eight minus 3, so this becomes 3 times 3 minus 8. 8 is 13 minus 5. Oh, then we again are having 5. What? 5 plus 3. What I am trying to show is that a linear combination of 8 and 13 is equal to 1, where the integers are 1, but I can't seem to be able to figure out what the linear combination is. So what I am trying to do here is I am trying to use the Euclidean algorithm to find the GCD and then running the calculation backward to find that linear combination, but I think I have messed up here somewhere. 13 is 8 plus 5, fine. 8 is 5 plus 3, 5 is 3 plus 2, and 3 is 2 plus 1. Okay, so 1 is equal to 3 minus 2, we have used this, and then 2 is equal to 5 minus 3, so this becomes 2 times 3 minus 5. Okay, then 5 is 8 minus 3, so this becomes 3 times 3 minus 8. Okay, then oh no, I think I have done the mistake here itself. Here I am substituting for the remainder 2 and I have written 5 minus 3. Okay, then I have to substitute for the remainder 3. Okay, yes, that's why it's not coming. After this I have to substitute for the remainder 3. So that will give me 8 minus 5. So this is 2 times 8 minus 3 times 5. Okay, so and now I have to substitute for the remainder 5. 13 minus 8. So this becomes, oh yes, yeah, this did not come to my mind, because 5 times 8 is 40 and 3 times 13 is 39, so that gives us 1. So this belongs to 8, 13. Now the moment 1 belongs to a subgroup of Z, every integer belongs to that subgroup, because you can add 1 as many times you want to show that every positive integer belongs to the subgroup. Take its additive inverse, the corresponding negative integer also belongs to the subgroup, and the subgroup, because it's a subgroup, it must also contain 0. So this contains all the integers. Hence, is equal to 1, which is nothing but the entire group of integers. And let's forget about this embarrassing calculation. C. In part C we have 6 and 15. Note that and 15 belong to this, and minus 12 suppose 2 belongs to 6, 15, then 2 is equal to 6n plus 15m for some integers n and m. Okay, 2 is equal to 6n plus 15m. Since 3 divides 6n plus 15m, we should have 3 dividing 2, a contradiction. So 2 cannot be contained in this subgroup. Next, suppose 1 belongs to 6, 15, then 1 is equal to it. Same thing, you can almost see what we are going to do here. 6n1 plus 15m1 for some integers. We could have just written similarly, we can show that 1 does not belong to this, but I just wanted to show that the similarity to you for ones, some integers n1 and m1. Since 3 divides 6n1 plus 15m1, we have 3 dividing 1, a contradiction. So 1 does not belong to this either. Thus 3 is the smallest positive integer in 6, 15. This implies that this is equal to 3. Okay, so it equals the cyclic subgroup generated by 3 in the ring. In the additive group of integers. Okay, now what happens if we have two arbitrary integers n and m? Note that n and m belong to, so if we proceed similarly, let's just see what we get. Now there exist integers, suppose alpha and beta, such that I need ink. Such that the GCD of n and m is equal to n alpha plus m beta. This implies that the GCD of n and m belongs to this. Okay, now we want to prove that this is in fact the smallest positive integer contained in this subgroup. Suppose, keep in mind that GCD by definition is a positive integer. Suppose there exists a positive integer k less than the GCD of n and m, such that k belongs to the subgroup generated by n and m. Then there exist integers. What should we take? Let us take u and p. Such that k is equal to un plus vm. This is because k belongs to this subgroup, okay, and a general element in this subgroup looks like this, and a linear combination of n and m where the coefficients are integers, in this case u and p. Now, since GCD of n and m divides n, and at the same time it also divides m, we must have GCD of n and m dividing un plus vm, that is this dividing k. This, however, is impossible because k is a positive integer strictly less than the GCD. So how can it divide k? Thus, our supposition that such a k exists is wrong. So that means no positive integer less than the GCD can belong to the subgroup. In other words, this is the smallest positive integer contained in the subgroup. Hence, so this is the cyclic subgroup generated by the GCD of n and m. And note that for this to be meaningful, both n and m have to be, at least one of n or m has to be non-zero, or both must be non-zero. If both of them are zero, then GCD itself does not exist, and in which case the subgroup generated is also the trivial group consisting of only the additive identity 0. Identity 0 because we are in a group. Okay, and finally we have this also, part E. Part E, I will just simply mention, you try to supply the details. Here, instead of 2 integers, we have 3 integers. And here also, this subgroup equals the cyclic subgroup generated by 3, where 3 is the GCD of 12, 18 and 45. Now, why this is equal to 3, you try to prove that. Okay, I will leave it to you. Then exercise 40, and just give me a moment. Exercise 41. prove theorem 3.6. So in theorem 3.6 we have to prove that the centralizer of any element is a subgroup of the group. Okay. So let us excuse me, let G be a group and let A be some element in G. Since AE is equal to EA, where E of course is the identity in G, we have E belonging to the centralizer of A. This in particular shows that CA is non-empty. When you want to show that a subset is a subgroup, always never forget to first of all show that the subset is non-empty. Now let X and Y be two elements in CA. Then X commutes with A and Y also commutes with A. Thus, what about XY? Y, this is equal to A XY, which implies that XY belongs to CA. So CA is closed under the operation in the group. Next, we have XA equal to AX. This implies you pre-multiply both sides by A inverse, that gives you A inverse XA equal to X, and then post multiply both sides by A. I mean again by A inverse. This implies, so X, no, I think, okay, this is not what I should have done. What the hell? Not A inverse. I should have pre-multiplied by X inverse. That would give me A equal to X inverse AX, and then post multiply both sides of this equation again by X inverse. So that will give me AX inverse equal to X inverse A. Yes. Now this implies that just like X inverse also commutes with A. So X inverse belongs to CA. So every element of CA also has its inverse in CA. Hence, CA is a subgroup of G. So this completes the proof. If H is a subgroup of G, okay, now just like the centralizer of a single element, we can define the centralizer of an entire subgroup itself. If H is a subgroup of G, then by the centralizer CH, C of H of the subgroup H, we mean the set of all elements X in G such that XH is equal to HX for all H in H. That is, the centralizer of H consists of those elements in G that commute with all the elements of H simultaneously. If X fails to commute with even one element of H but commutes with, say, many other elements of H, then it will not be in the centralizer of H. Prove that CH is a subgroup of G. Okay. Since EH equal to HE, keep in mind that unlike the centralizer of a single element, now the condition that is to be satisfied is more stringent. It requires more. We want the element that we are going to put in the centralizer to commute with all the elements of H. Okay, so that must be true. Since EH is equal to HE for all H belonging to H, where E is the identity of G, we have E belonging to the centralizer of H. And this in particular shows that CH is non-empty. That thing is understood. We are not going to write that again and again. Now, let X and Y be two elements in CH. Then actually we could have solved this slightly differently, but anyway, let's just proceed with what we have now. Then XH is equal to HX and YH is equal to HY for all H belonging to H. Okay. This implies, you can see that from this point on, we just are going to repeat these things. The only difference is that here we had a single element A, here we are having all the elements H of capital H. This implies XYH is equal to XYH, which is XHY, that is equal to XHY, that equals HXY, and that equals HXY for all H belonging to H. This implies, or we can just simply write hence, XY belongs to CH. Also, XH equal to HX implies, okay, this time I have to be careful. I want inverse of X, not H. H is equal to X inverse HX, that is equal to HX inverse, that implies HX inverse is equal to X inverse H for all H belonging to H. Thus, X inverse belongs to C of H. Hence, C of H is a subgroup of G. So this was 42. Now 43. Must the centralizer of an element of a group be abelian? That is, if you have a group, you choose one element from the group and then you find its centralizer. Is it necessary that the centralizer as a group is always abelian? And the answer is no. In the group, in the dihedral group D4 of symmetries of a square, the centralizer of this rotation, you can go to the Cayley table for D4 and you can see that this particular rotation commutes with every element of D4, so that the centralizer is D4 itself, and we know that D4 is not abelian. So it's settled negatively like this. So if not centralizer, what about the center? Must the center of a group be abelian? In this case, yes, it is true. Yes, let G be a group for any x and y belonging to the center of G. We have xy equal to yx. And why is that so? It's because you recall that an element is in the center, or an element is a central element if and only if it commutes with all the elements of G. In that sense, if you combine the definition of the center and this centralizer of a subgroup, the center of a group is actually what I'm trying to say, the center of a group is it the centralizer of something? Isn't it the centralizer of the whole group? Because you see, according to the definition of centralizer, CH consists of those elements of G that commute with all the elements of H. In that sense, CG will consist of those elements of G that commute with all the elements of G. In other words, central elements. So yes, ZG is equal to CG. So you can see that because X is a central element, Y is also a central element, but we only need one. So xy must be equal to yx because x commutes with all the elements of G. In particular, it will also commute with y. So we can, in fact, as an interesting note, you can write this. Okay. This note, however, does not have any place here. It should have been written here. Exercise 45. Let G be an abelian group with identity E and let N be some fixed integer. Prove that the set of all elements of G that satisfy this equation is a subgroup of G. Give an example of a group G in which the set of elements of G that satisfy the equation does not form a subgroup of G. Okay. So there, of course, there are many more exercises in this set of exercises. So let me just end the video here itself. We will continue in the next video. So that's it for Gallian in this video. This is me, Lucifer, from a mathematical room. Have a nice night.